All right, good. So at the conclusion of the last talk, there was a question about free-floating planets and microlensing. And that turns out to be a great segue to what I'm going to talk about, because I'll spend the last third of my talk talking about how we can learn about free-floating planets, not just from microlensing, but also from results from other detection techniques like radio velocity and direct imaging as well. So you'll want to be sure to stick around for that. We know that exoplanets exist, and we know that planet formation is not unique to our own solar system, but rather it's a general phenomenon. Over the past couple decades, we've learned that exoplanets are ubiquitous and diverse. However, we're still working to characterize this diversity to determine the true distributions of the fundamental properties of exoplanets and how these properties depend on those of the host stars they orbit. This turns out to be a difficult project because exoplanet detection techniques are not sensitive to the full range of exoplanet parameter space. So there have been some planets that have been detected directly via high contrast imaging, but a vast majority of our planets that we know about have been discovered by measuring variations in a few different observables. So either the centroids of absorption lines in host star spectra via the radial velocity method, or variations in the apparent brightness of the host stars via the transit method, or variations in the magnification of a background source star that happens to be near our line of sight to an exoplanet host star. Now, the physical processes that produce the observables for these different detection techniques are fundamentally different, and so too are the properties of the systems that each of these discovery techniques can reveal. And so in other words, what this means is that the different detection techniques are sensitive to planets that lie in different regions of planet parameter space, and are also sensitive to different physical parameters of the planets themselves. And so now I'm showing another version of the same mass separation diagram as I showed before, only now I've broken it down by detection method. And so in the background, you'll also notice some shaded regions here, and these represent approximate schematic representations of typically where these different detection techniques are sensitive. And so you have radial velocities here in the green and transits in the blue that are sensitive to the closer separation planets, whereas up here in this region shown by the red square, you have this region of sensitivity for direct imaging surveys. And sort of bridging this gap at intermediate separations, you have the microlensing detection method. Now, in reality, these sensitivity regions are not sharp, straight lines, but rather have some structure to them. And these are manifestations of various selection effects and observational biases that are intrinsic to each of these different detection methods. And it turns out that we need to take this into account if we want to determine things like exoplanet occurrence rates. And if we do want to solve such a problem as how common are planets, if we use results from an individual technique, then our results will be constrained to these limited regions of planet parameter space. But to learn about planet formation and the physical processes at play in planet formation, we really need to be constraining these physics by trying to determine an exoplanet census that is valid across as wide a region of this parameter space as possible. And that's precisely what my research focuses on, to develop a statistically complete, or at least as complete as possible, given the current available data, and an unbiased exoplanet census by synthesizing results from multiple different detection techniques. And so in my research, I choose to focus on M dwarfs for a couple reasons. First of all, they're the most common stars in our universe. And secondly, and perhaps surprisingly, they're also the most well-characterized stellar population in terms of exoplanet demographics. And this is due in large part to the fact that the constraints that we have from microlensing, which bridge the gap in sensitivity from the smaller separation planets covered by transits and radial velocities, and the larger separation planets covered by direct imaging, these constraints for microlensing exist primarily for M dwarfs. And this is simply because the rate of microlensing events depends explicitly on the mass function of lenses, which is heavily weighted towards lower mass objects, and thus most of our lenses will be M dwarfs. And finally, there exist several observational constraints from each of these different techniques on planet occurrence rates. And let's now go back to this mass separation diagram. And here I'm only showing the confirmed exoplanets around M dwarfs. And so one thing you'll immediately notice is that the number of planets that have been discovered around M dwarfs is much smaller than the full sample. However, there's still quite a bit of planets here. And I should mention that in this talk, I will focus on results from radial velocities, microlensing, and direct imaging, and I won't say too much about transits until I get to the end. And so here are a couple results from demographic surveys, demographic studies that have been derived from these different detection methods. And so we have some upper limits on giant planet frequency from direct imaging surveys. And here in the green are results from radial velocity surveys, which measure the frequency of giant planets across the regions that are shown by these horizontal bars here. And the vertical error bars are the actual measurement errors on the planet frequency itself. And so you can see that radial velocity surveys infer a frequency of giant planets that is low. And this is consistent, at least qualitatively, with the predictions of core accretion theory of giant planet formation, which predicts that giant planets should be relatively rare around lower mass stars. But now, on the other hand, we have these results from microlensing, which seem to imply that giant planets are actually very common, albeit microlensing is sensitive to planets that are somewhat less massive than those probed by radial velocities at longer periods, but nevertheless still giant planets. And so this order of magnitude difference between these two results creates a lot of tension between the two. But drawing such straightforward conclusions from these two plots alone is very dangerous because there's a lot of stuff going on here. There's a confluence of various selection effects and observational biases that confuse such a straightforward interpretation. And so this prompted a careful study to actually do a robust comparison between RV and microlensing results. And so now I'm just going back to show where these two different types of surveys tend to be sensitive. You'll notice that while they're disjoint, there is a significant region of overlap between these two methods. And so to really test if the results that we're getting from these two different types of discovery techniques are consistent, what we want to do is check the occurrence rates that are measured by both of these types of surveys in this region where they overlap and see if you get the same answer. So to do this, I'm starting out by assuming the population of planets that is inferred by microlensing surveys and positing that they exist around a sample of radial velocity monitored stars. And so this is the distribution function for the microlensing inferred planets. And this is a function of Q, the planet-to-star mass ratio, and S, the projected separation in units of the Einstein radius. So these are the two routine observables in a planetary microlensing event, as we heard from Jennifer in her talk before. Now, the parameters of this distribution function have been measured from a couple different microlensing surveys. So the slope specifically was measured by the Sumi et al. Survey in 2010 from MOA data. And the normalization of this distribution function comes from a combination of that survey plus a microlensing study done by Andy Gould and others, also in 2010. And so central to this idea of comparing the two results from these different surveys is being able to map the properties of this population of planets inferred by microlensing into the space of observables for radial velocity. And so specifically, we have the task of mapping the mass ratios and projected separations into the velocity semi-amplitudes and orbital periods of these planets. Now, as Jennifer mentioned in the previous talk, we don't measure a lot about the host stars of microlensing events in a majority of cases, and so we must appeal to statistical arguments in order to get this mapping here. And so we must do things like assume a model for the galaxy and assume a lens mass function. And we must also generate orbits for each of these different planets, because in microlensing we don't typically measure any orbital parameters of these planetary systems. And so we must adopt some priors on each of these orbital parameters and use those in conjunction with our galactic model and our lens mass function, as well as the rate equation for microlensing events to generate a likelihood function that we can then use to determine the joint distribution of the radial velocity observables. And so when you do such a thing, these are the results you find. And you can see here that for microlensing planets, they tend to have a period of about 9.5 years and produce an RV semi-amplitude of about 0.2 meters per second. And if you know anything about radial velocity surveys, you'll know that immediately most of these planets will not be detectable by radial velocity surveys. Sort of at best, you can get about a meter per second precision with current state-of-the-art facilities. However, remember, these are for M stars, and so M stars tend to be quite noisy and have something like 3 to 6 meters per second of stellar jitter that you also have to contend with. And so now here I'm just plotting some median sensitivities for a couple different radial velocity surveys, and these lines are constant signal to noise for a detection. So this teal line here represents the HARP South median sensitivity curve, while the yellow shows the same thing for the CPS trend survey. And so if we look at the marginal distribution of orbital period for these microlensing planets, you can actually see that in terms of just the orbital period, these radial velocity surveys have been ongoing long enough to be sensitive to a majority of the planets which microlensing routinely discovers. However, if we look at the marginal distribution of the velocity semi-amplitudes, you can see that we're only picking out part of this tail of this distribution, and these are the high mass planets, Jupiter mass and above. And so now what we do is, since we have actual sensitivities for these surveys, and in fact we have individual sensitivity curves for each of the stars in these two radial velocity surveys, we can determine the number of these planets that we would expect them to detect given the microlensing population. And so when we compute this number of expected detections and compare them with what they actually detect, in the case of the HARP South survey, we expect them to detect about one planet with a mass between 1 and 13 Jupiter masses and an orbital period between about 3 and 10 years. And indeed, they find one such planet. Doing the same thing with the CPS trend survey, we expect them to detect about 4 or 5 planets, and indeed they detect about 4 planets, or they detect exactly 4 planets. And the planets that we predict and those which they actually detect have very similar masses and orbital periods as well. And so what this means is that this large apparent discrepancy between these two sets of results is actually not a discrepancy at all, but rather the numbers of giant planets they infer, or the frequencies of giant planets they infer, are quite different simply because of the very steep planetary mass function measured by microlensing surveys. And again, I'll just point out that this is dn d log q, and so this is a very steep function. And so at longer periods where microlensing is primarily sensitive, radial velocity surveys can only detect the most massive of those companions. So now that we've shown that these two different methods give you the same answer in the region where they overlap, we can synthesize their results and basically do some addition to determine occurrence rates across the entire range of planet parameter space spanned by these two different techniques. And so when doing that, these are the results that we find. And so there's a lot going on in this figure, so I'll kind of just break it down a little bit. And so there are regions where we have upper limits on planet occurrence rates, and these come from areas where we have sensitivity, but we discover no planets, and so only have an upper limit. There are regions where we have lower limits, where the sensitivity of these various surveys begins to drop off, and so we only catch sort of a corner of a square or something like that, and regions where we have both. And so now if I overplot where these sensitivity regions are for the two different techniques, you can kind of see why this figure is the way it is. Now we can do better than that, and then specifically we can improve our constraints on massive long-period planetary companions to M dwarfs by including results from direct imaging surveys. And so the idea here is to improve our constraints in this upper right region of this plot here. And so that moves me to the next part of my talk, doing a joint analysis of results from microlensing RV and direct imaging surveys. So here are the sensitivity regions of the various techniques that I'm going to look at. And now I'm interested, since I care about long period planets, I'm interested in the long-term radial velocity trend detections. And so this green region here shows where current RV surveys, roughly where they're sensitive to long period trends. And so in this survey, or in this study, I include results from 5 different surveys that employ these 3 different independent detection techniques. And the primary question I want to ask and to answer is there a single planet population that can simultaneously explain the results of all of these different surveys I consider? And so before, when I was comparing microlensing with radial velocities, I started out by assuming the microlensing planet population. Here I'm doing something different. I'm assuming a general planet population model described by 4 free parameters here. And so these free parameters are alpha, the slope of the mass function, beta, the slope of the separation distribution function, A, which is the normalization of this entire distribution function. And then this parameter here, A out, which is an outer cutoff radius for the separation distribution function. And so you can think of this as either, the maximum semi-major axis in a disk out to which planets form, or the maximum semi-major axis out to which planets after they have formed have migrated, or the edge of your protoplanetary disk, whatever you like. It's just a free parameter of our model. And so what we do is to take a random set of these parameters and generate a population of planets. And so these planets are now described by masses and semi-major axes, and then we have to do the same problem as before of mapping into the observable spaces for each of these different detection techniques. So in the case of microlensing, we're doing the inverse mapping of the one we looked at before, where we start out with masses and semi-major axes and go to mass ratios and projected separation in units of the Einstein radius. And so, of course, this mass ratio is a function of the planet mass and the host star mass. And the projected separation is a function of orbital parameters, the mass of the host star or lens, the distance to the lens, and in principle, the distance to the source, although that matters much less. And so, again, we don't actually know what any of these things are, so we must appeal to statistical arguments, our model for the galaxy and our lens mass function, and the rate of microlensing events to generate likelihood functions to get our distributions of mass ratios and projected separations. Now for radial velocities, and in particular since we're interested in long-term trends, we need orbital periods and we need to compute the acceleration that the host star would feel as a result of such a long period planet. And so here this is again the mapping that we need to do. And so we know how to deal with orbital parameters. We just generate them, the orbits randomly, and then at the end we can marginalize over all of these nuisance parameters. And in the case of rate of velocities, we're often able to measure or at least estimate the masses of their lens stars. And so we have these in hand, complete with uncertainties. And so we simply sample our distribution for the host star mass for each of the radial velocity planets. Now, in the case of direct imaging, we need to determine a difference in magnitude between the planet and the host star and a projected separation, this time either in arc seconds or in AU, whichever you like. So to do this, again, we need orbital parameters to project our orbit. And we need a distance to the host star itself. And we need an H-band magnitude or a magnitude in some band for the host star. We can measure these two things. And so here the key parameter that we really need to figure out is what is the magnitude of the planet, the absolute magnitude of the planet in some bandpass that's the same as the host star. So for example, again, H-band. And so in order to do this, we must appeal to planetary evolutionary models. And so in general, there are two classes of these models, so-called hot start and cold start models, which are sort of concomitant with different planet formation scenarios. And so, since we have an estimate of the age for the star, we assume, there was a question about this earlier, we assume that the planet and the host star are the same age. And we can determine since we know the mass of the planet, we can determine a magnitude for this star, and that then directly allows us to compute this magnitude difference. And so now that we have done all that, we can actually apply the real detection limits from these actual surveys to determine how many planets you expect to detect in each of these different cases. And so here I'm just showing some examples of these detection limits for these very different types of surveys. And so doing this for many, many different populations, we can develop constraints on these parameters and see if there's any class of this model that can actually explain the results of all these different surveys. And when you do so, these are the results that you get. So you can see that we can constrain alpha, which again is the slope of the mass function, and A, the normalization, quite well. However, we can't develop constraints on beta, the slope of the separation distribution, and A out nearly as well. And there are some reasons for that, and there's actually a lot that goes on in these contours. I don't have time, but just to give you a little bit of a taste, I'll explain a couple features. So you'll notice that there's a pretty sharp lower limit on beta, the slope of the separation distribution function. And this comes from the fact that we require our planet population to produce some long-term radial velocity trends. And so for very negative values of beta, you have distributed all of your planets in at short separations, where they're certainly able to be detected by radial velocity surveys, but in that case, they would be detected as actual detections and not long-term trends. In other words, you get a full orbital period for such planets, and that's not what we require. Now, you can't actually put an upper limit on the value of beta from rate of velocities. And so this is where direct imaging starts to kick in. So if you look at this contour here, this is the outer cutoff radius of the separation function and its slope. You'll notice that for separations less than about 13 or 15 AU, you can actually have any value of your separation distribution slope that you want. And the reason for this is that the inner working angle for the direct imaging surveys that I assume is about, at their typical target distances, is about 13 to 15 AU. And so since none of these surveys actually detect any planets, no matter what your other parameters of your planet population are, you're always consistent with the direct imaging surveys. Now, as you allow this outer cutoff radius to move into regions where direct imaging surveys are sensitive, you must compensate for that by shallowing out your planet distribution, separation distribution function. And so what this all means is that, in fact, there are sets of these populations which explain all of the results of these surveys I detect. And here I'm just showing the marginal distributions of each of these parameters. And this just lists some of the median values and 68% credibility intervals for the different parameters of this model in both the hot and cold star cases. So now we can use this information to update our demographic constraints on exoplanets around M dwarfs. And so you can see that we've gotten rid of our lines in these two boxes up here. And now I'm showing in regions that are shaded with these sort of vertical bars, these are areas where we have no sensitivity to planet detections from any survey, but so instead what we've done is we've extrapolated. And so I would say that if you're going to use these results in this extrapolated regime, do so, at your own discretion. And so this brings me to the last part of my talk, which is how can we use this information, as well as other information from microlensing, to constrain the galactic population of free-floating planets. Now, I just mentioned that we have no sensitivity to planet detections in this region down here, but it turns out that's not actually strictly true. And in fact, we do have some sensitivity to planet detections there. However, the catch is that when we detect these things, we detect them as free-floating planets with microlensing, as single-lens events. It actually turns out to be a very difficult problem to distinguish wide separation planets, very wide separation planets from free-floating planets. And this is just due to geometry. And so I'll tell you a little bit about that. But first, let's look at some MOAA data from 2006, 2007. This is a distribution of event timescales for a sample of events. And this was originally published in SUME 2011, the study that Jennifer Yee had mentioned in her previous talk. And so if you want to explain this, you can start out by assuming a lens mass function. And so what I've done here is I've assumed a lens mass function comprised of a population of brown dwarfs and main sequence stars, as well as stellar remnants, including white dwarfs, neutron stars, and black holes. And here you can see the contributions to the timescale distribution from each of these different populations. You can see that for the long timescale events, we're actually doing very well. We can explain most of them quite well. And I should point out that this is not a fit to this curve. This is a model prediction. The only sort of interaction between this observed data and the prediction is that in the total number of events. They've been normalized to the same total number of events. And also, our predicted curve has been corrected for the detection efficiency of microlensing events as a function of the timescale. But one thing that you'll notice immediately is that there's an overabundance of short timescale microlensing events. So for timescales less than about 2 days, we've actually observed 10 events, but our predicted model only expects about 1 or 1.5 events. And so what SUME had done originally when he published this observed timescale distribution is to assume sort of an extension of the lens mass function down to the planetary mass regime, and assume that these were free-floating planets. And so what he tried to do was to figure out, what the mass of these things should be and how abundant they must be in order to explain this observed timescale distribution. And so here again, these dashed lines are 2 different lens mass functions, and the 2 dotted lines are the corresponding free-floating planet mass functions that he used to fit this distribution. And so from this analysis, he deduced that there must be almost 2 free-floating planets per main sequence star. Now, this is quite a large number, and it's very difficult, it turns out, to explain how these things have formed and how they came to be free-floating planets. And so another feature of these short timescale microlensing events is that they show no evidence of a primary lens or a host star in their microlensing light curves. And so there's a few different ways where you can infer the presence of a host star in a wide separation microlensing event. And so we'll look at 2 of them here. One is a low magnification primary bump, and the second is by looking at events where the source crosses very near to or even crosses the planetary caustic. And so first I'll just sort of set up the situation here. So assume we have some bound planet separated by its primary lens by some projected separation S. And now I'm just drawing the planet-to-star axis on here. Now there will be some planetary caustic at a position S minus 1 over S. And again, here in this case, since we're looking at wide separation planets, the assumption is that S is much greater than 1, or the projected separation is much greater than 1 Einstein radius. Now assume we have the source coming in on some trajectory shown by this blue curve here. It's going to have some impact parameter to the primary star, to the primary lens of U star. Now there is a threshold impact parameter where if your actual impact parameter is larger than this value, then you won't be able to detect any magnification due to the host star. And this threshold impact parameter depends on the parameters of the microlensing survey itself, so the photometric precision, the observational cadence, and things like that. And also it's very weakly dependent on the mass of the primary itself. And so in this particular case that I've drawn here, all we would really see is the event due to the planet that looks like a single lens event and nothing else on either side. If, however, the impact parameter to the primary is less than or equal to this threshold impact parameter, we'll begin to see this low magnification bump. And so this tells us that there is another body in the system and that it's the primary to the planet that we have detected. And the bump can either be on the right side or the left side, depending on the direction the source travels. In this case, I've drawn it going up and to the right, and so it occurs at a time later. And so this means that there is a range of source trajectories for which you can detect the source through such a low magnification bump. And don't worry too much about the form of the equation, just as long as you understand qualitatively what's going on. There's some range of angles for which you would expect to detect the primary through such a process, and you can work out what the probability of that is. Now, another way you can distinguish free-floating planets from wide separation bound planets is by looking at looking for anomalies near the peak of the microlensing event. And so as you have the source come by, it has some impact parameter to the planetary caustic. And this planetary caustic has some size, which I've labeled here as theta c. And it has some form that depends on the mass ratio of the planet to the star and its projected separation. And so if this impact parameter, if the source trajectory goes sufficiently far away from this planetary caustic, then again, you'll just see something that looks like a single lens event, and you won't be able to tell if there's a host star or not. If, however, the source passes sufficiently close to one of the cusps of the caustic, or even flat out crosses the caustic, you can get effects that allow you to infer the presence of a host star, because such a feature is very indicative of a binary lens or a multiple lens. So this allows you to infer the presence of the primary star. And again, you can work out what the relative rates of such events are to normal microlensing events. So now this is just a plot of the fraction of microlensing events where you expect to see signatures of a primary. And so the blue dotted line shows where you expect to see primary bumps, and this red line here shows the same thing for planetary caustics, and the black line is either one. And so this, by the time you get out to about 5 Einstein radii, you've dropped to something like 50%. And then when you get to about 10 to 20 Einstein radii, you're down to about 10% of events where you expect to be able to distinguish wide separation from free-floating planets. So now the problem becomes, can we use what we've learned before from microlensing, RV, and direct imaging to try to explain the observed timescale distribution of events using bound planets and not having to appeal to free-floating planets, or at least some fraction of these things. So we take as a prior to our analysis these populations of planets that we know to be consistent with all of these other surveys. Determine which ones you expect to not see signatures of a primary in the light curve, because of the 10 short timescale microlensing events, there are none, and so we want to reproduce that. And it turns out that you can do somewhat reasonably well. You can explain some of the shorter timescale microlensing events with these bound planets, but not all of them. And so this allows you to constrain the fraction of short timescale microlensing events that must be due to free-floating planets. And here I'm just showing the 68%, the maximum likelihood and 68% credibility fits to this observed distribution. And so here are our constraints on the fraction of short timescale events due to free-floating planets. And so for the hot start planet models, planet evolutionary models, we find a median of about 67% of the short timescale microlensing events must be due to free-floating planets. In the case of cold start, it's about 58%. And here you can see the 68 and 95% credibility intervals on this as well. Now, if you want to actually convert this into a number of free-floating planets, it turns out that you must assume something about the mass function of these free-floating planets. And so what I've done is I've just done the simple exercise that Sumi had done, and assuming that these are a delta function in mass, and determining how many of these you would need to explain the residuals when you subtract off the contribution due to these bound planets. And it turns out that you can best match those to, you can best explain the residuals by a population of free-floating planets about 1.5 or 2 Jupiter masses, and you would need about 1.4 of them in the case of the hot start models, or about 1.2 in the case of the cold start models. And again, these are the median values, but it could be as low as 0.5 free-floating planets per main sequence star for hot start models, or even as low as 0.3 in the case of cold start models. But this just shows the full posterior on this value. Now, just very quickly, I'll summarize by looking at some future prospects for research in synthesizing results from different methods. Now, I mentioned that I focused on RVs, microlensing, and direct imaging, but transit results are very informative as well. They allow us to probe at shorter periods very low mass planets, very small planets. And so that would be very useful to include in our analysis. And so the next step in my work is to include results from transit surveys, and in particular, those from Kepler. But even once that's done, you'll notice that we're still not sensitive to a majority of solar system analogs. So we still have to appeal to things like extrapolating our results and other things to determine the relative frequencies of solar system analog planets. But there is good news. There's a microlensing survey that's proposed with WFIRST, and this dark blue curve shows the expected sensitivity of such a microlensing survey. And you'll notice that we will now have sensitivity to a lot of the analogs of the solar system. And in fact, combining results from WFIRST with those from Kepler will pretty much completely fill out the exoplanet census and solve the problem. There's also a proposed direct imaging mission for a proposed telescope called the High Definition Space Telescope that was written up in the Aura report from last year that could also help to provide constraints. And with that, I'll thank you very much, and I'll take any questions.
Thanks, Jason. Questions? Yes.
So I have a question about your posterior distributions. Can you put this slide up? So this one, as a very present person, what this is telling me that if I want to help you, I really need to push more on the angular separation than deep in contrast.
So actually,
True or,
what I recommend to do is, in fact, to go deeper on individual targets. So in other words, spend more time on a fewer number of targets than trying to go for a multiple number of targets, because it turns out that actually adding more upper limits on planet frequency at the same depth doesn't help you that much. However, since we know that this mass function is very steep, preferring very low mass things, if you can start to decrease that sensitivity limit to lower masses, then since this is such a steep power law, you suddenly start to pick up many different planets, or at least test if this mass function is true out at larger separations. Yeah.
More questions?
So I guess your question is, do I care about the metallicity of the microlensing sample stars?
Yeah, I mean, it can be different from the RV selected stars.
Yeah, that's certainly true. The metallicities for the microlensing stars are almost certainly different from the local radial velocity samples, and especially the even more local direct imaging samples. There's a measured metallicity gradient throughout the galaxy, and this has been done through Segway and Apogee as well. One thing I didn't have time to discuss was that I don't actually assume anything about the metallicities for for any of the microlensing stars, and yet I'm still able to show that the frequencies you get from microlensing and radial velocities are consistent. I did another step in the paper that I actually wrote that up in, where I took this measured metallicity gradient from Apogee. There's a paper by Hayden et al., I think in 2014, that provides sort of a metallicity map of the galaxy. And so folding that into my Bayesian analysis that I had done to determine all of the other properties of the lens systems, I also determined a metallicity for each of those things depending on its location in the galaxy, both radially inwards and also height above the plane. And when you do this, you can determine some distribution for the metallicities of microlensing host stars, and you find that it has a median metallicity that's very high of about 0.17 dex. And so if you then do the exercise of plugging those metallicities into the radial velocity determined giant planet metallicity correlations, you would find that those relations would predict that you expect to find many more planets than microlensing actually detects. So this is sort of the opposite problem of what we thought we had before, where microlensing predicted too many. And so this is sort of an open question and a mystery that I don't actually know the answer to. I have some ideas, but... So the question is, how does my planet occurrence model deal with multi-planet systems? And the answer to that is, in the data that we used, we were dealing with mostly single planet systems. So that's not particularly something that we had to worry about, at least at this time. But you're right, that is sort of an issue, how are you going to deal with that? And in particular, when I go to include results from the Kepler survey, that's something I'm going to have to think about very carefully. And I don't actually know how to do that just yet.
Time for one more question. No more questions. Then, many thanks again.